Today, we are going to be fine-tuning a large model using two separate data sets, and I'm going to show you how to use LoRA, how to write code to do the fine-tuning process extremely efficient. Here's what's really cool about LoRA. Not only makes fine-tuning way faster, but it also generates these small adapters that you can plug and play together with your model to get your model solve specific tasks. Okay, so when you think about this, Apple is about to release Apple Intelligence. I'm going to show you right now what they say on the blog post that they posted, so you can see how smart it is what they're doing. That is exactly what I'm going to show you how to code today, so you can do the same thing. So let me go to the website and show you what I'm talking about. This is the machine learning research blog from Apple. And there is a section, you can read this article if you want to, it's called Introducing Apple Foundation Models. So they're talking about their big models that they're gonna be shipping inside the phone in your pocket, okay? So there is a section that's called model adaptation, and I think it's great. So they say, our foundation models are fine-tuned for users' everyday activities. So basically, they have a foundation model, and they did fine-tuning for a bunch of different things that they want to use that model for, like email summarization or email replies or query handling. Like there are multiple tasks, and they're doing the fine-tuning process to adapt that foundation model to the process, to the specific tasks, and can dynamically specialize themselves on the fly for the task at hand. This sentence here, it's like magic. They have foundation models, they fine-tune those models, and they're telling us that those models can specialize on the fly. That sounds pretty cool. We utilize adapters. We're gonna be building those adapters today. I'm gonna show you how to do that, and I'm gonna show you, more important, how they work. Small neural networks modules that can be plugged into various layers of the pre-trained model. So they have a pre-trained model, that's the foundation model, that's the big model, that's the heavy model, and they have these small adapters, and they're telling us that they can take those adapters and plug them with the foundation model to get the model act different, to fine-tune our models for specific tasks. So that's basically the way it works. That's what they're doing. That is what I'm gonna be showing you how to do. Now, here is my code, and you have access to this whole notebook. You're gonna find a link below in the description somewhere. Here I'm using Lightning Studio, which is amazing if you really want to use GPUs. And obviously, because I'm gonna be training a large model, I'm gonna need GPUs. As you can see, this is just Visual Studio in the cloud, okay? So this is the way it works. If you're familiar with Visual Studio, well, you are familiar with this. You can see that here I'm just running this, and I'm gonna go through this whole explanation just using the CPUs, because I don't want to be spending credits on GPUs. But if I wanted to switch to GPU, I can just click there, click on switch to GPU, and here are the options that I have. I trained my models, I fine-tuned my models here using an L4. I think it took about 5 minutes to fine-tune both models, maybe a little bit longer. And that was pretty decent, and I had to pay 70 cents per hour just to get that done. Okay, so not a big deal. Let me go back to the code. Let me hide this, and we can go down this notebook. It's gonna be pretty simple, but before I get into the actual code of how this works, I wanna show you a few slides that I put together just so you understand how freaking awesome this is, okay? So, why do we care about fine-tuning, and why do we care about LoRA? Why is it important? Well, at the beginning, the whole idea is to get a foundation model, which is gonna be large, it's gonna be heavy. We want to fine-tune that model to specialize that model. So now, in the case of Apple, these are some of the tasks that Apple wanted to specialize their foundation model on. So, mail replies. They want a model that's capable of producing replies to an email, right? Summarization, proofreading, query handling, there are many other tasks. So you get your foundation model, You make your foundation model better at those tasks through a fine-tuning process. So that's just a regular fine-tuning as we know it. Now, here's the thing though. What Apple is telling us is that they're not creating copies of a foundation model, copies that are specialized on different tasks, which is what you will get from a regular fine-tuning process. Instead, they're talking about adapters, which are small neural networks that they can plug into different layers of the foundation models. So in theory, what they're telling us is that their users are going to be using the same foundation model they created, plus small adapters that are going to make that foundation model act differently. And this is huge if true, right? So in the Apple's world, or in the LoRA world, because Apple did not invent this, they're just using this tech, they're gonna have these small adapters which are going to be helping the foundation model get specialized on different things. And more important than anything, they are going to be loading or plugging those adapters dynamically as the user needs to perform something. So they can have the foundation model loaded in memory, and depending on the task that they want to perform, they can plug and play one of those adapters. And that is super, super beneficial in comparison with the regular model where you actually have multiple copies of a huge model. So if you're trying to do summarization, you have to load this huge model in memory. If you're trying to now switch to proofreading, you will have to load this second model in memory. Remember, these models are really, really big, and the phone does not have that much memory. So having the idea of the adapters, something that is like a chip that you put together with the model, and the model switches. Now it can do something much better. That idea, I think, is genius. Now, how does this work? Okay, here is where we get a little bit behind the scenes, and this is what I want you to look at. So I have the foundation model original weights. Now, obviously, a model, one of these large models, they have multiple layers, and there are multiple parameters per layer. But just to simplify the idea, imagine that we had only just one big layer, okay? So it's just one huge matrix of parameters. In the case of the first one here, the first image that I have here, that will be the original weights of the foundation model. So these numbers instruct that model on how to do general tasks. That's what the model does, the foundation model. Now, I'm adding up here a new matrix, which is the same size, which are changes. So this matrix is that adapter that I was talking about. The adapter will tell the original weights how they need to change in order to give us the fine-tuned weights. So now imagine that I have two different tasks. I'm gonna have two different adapters, and each adapter will have just positive or negative numbers that added up to the original matrix will give us a new matrix that will know how to do a task better. That's the idea of an adapter. Something that I can dynamically load, do an addition, and get a new, completely new model that acts differently. But there is a problem, and this LoRA weight changes matrix here is the same size as the original one, but that's not what we wanted to build. What we wanted to have is just a small adapter, something that's really small, but here, this looks like a freaking copy of the whole model. So what's going on? Well, that's where the genius part comes in, okay? So the creators of the paper of LoRA, they realized that we can represent a big matrix as the multiplication of another two matrices that are smaller. Like for example, these LoRA weight changes, which have the same parameters that I have here, you can represent this matrix by the multiplication of these two smaller matrices. And you can do the math if you want to, just correct me here. But in this matrix, I have 25 values, but here I only have 10 because it's a column vector with 5 rows that will give me 5 values. And this is just a regular one row vector of another 5 values. So 5 plus 5, that will be 10 values. And those 10 values, if I multiply them together, will give me these 25 values. Do you see what I'm going with this? So the adapter is not this, which is huge, the adapter will be these two matrices here. So I can get, in the case of a model with 25 parameters, 60% in reduction, because 15 of those parameters I do not need. I don't need to store them. I don't need to represent them in any way. I only need these 10 values. At runtime, when I'm ready to load that adapter, I can load my foundation model, load the adapter, do the multiplication, which is a really fast operation. And after I do the multiplication, I'm gonna get the weight changes. And then I'm gonna get those weight changes and add them up, the original weights, to get the fine-tuned weights. And that will happen extremely fast in memory. And we can get a model acting differently without having to keep different copies of that model. And that is genius. Now I want you to see something else, which is gonna give you an idea of how impressively effective this is. I just put here a few examples of different model sizes so you see the savings. So for 25 parameters, which is just for illustration purposes, the savings are 60% because we only need 10 values to represent 25. For a model with 1 million parameters, the savings will be 99.80%. Just huge. How much space we are going to save, right? And for 2 billion parameters, which is considered today a very small model, the savings will be 99.995%. Because we will need, for 2 billion parameters, we will need approximately 44,000 times 44,000 matrix just to represent the same thing. And that will give us a total of approximately 88 or 89,000 parameters total. Now, keep in mind a couple things. So number one, remember, this is just for illustration purposes only because a model has multiple layers. So it's not like we only have a huge matrix. So we will have to do this multiple times. A LoRa adapter will not just be two matrices. It will be two matrices for each one of the layers where we want to apply LoRa. I'm just simplifying this so you think of it as a single big matrix because it's easier to explain. But the same principles apply. The savings will be humongous. The other thing that I wanted to mention is that it is very clear just by looking at this, hopefully, that the savings are huge. So in terms of storing this model or these adapters, we're gonna have like a huge decrease in memory and disk space. But that's not all of it. The creators of the papers also realized that we can actually, instead of trying during the fine-tuning process, instead of trying to fine-tune every single parameter individually, we can focus on finding or fine-tuning these two matrices here. So basically, we can take these two matrices and find values that multiplied, give us a list of changes that added up to the original model, get us closer to our objective. So the fine-tuning process is also getting a huge boost. And now we can fine-tune a huge model very, very quickly because we're only changing these few parameters here. So it's a double band here, right? We're getting our cake and we're eating our cake too. And that is super, super cool. And final thing that I'm gonna say before I go to the code, LoRa is not even the most efficient way of doing it. There is like a second version. It's not a second version, it's a different version that's called QLoRa, which does LoRa but quantized. I'm not gonna talk about that one right now, but just look it up if you wanted to see an even more efficient way of doing this. Now, let's see the code because that's where things get really interesting. To run this code, you have two options. So number one, download this notebook on your computer. You're gonna have to have a GPU or this is gonna take a long time, okay? The model is not huge, but still it's gonna take a long time if you want to do the fine-tuning process on your computer. So load this on your computer. All of the libraries that you need are specified right here, right? You're gonna need transformers, accelerate, evaluate, datasets, and parameter efficient fine-tuning. Those are all the libraries that you need. So just running this notebook will give you everything that you need. Or you can just go to Studio, just create a new account in Lightning Studio, and this is what you are going to get, right? And now you can use GPUs. You have a free quota, which is great. That'll be awesome. So what am I going to be fine-tuning here? I'm going to be fine-tuning a vision transformer. So basically, I have a large vision transformer that I want to specialize in two different ways. Number one, I wanted to improve it recognizing food items, recipes. Okay, so I have a data set of food items that I'm going to be using to fine-tune this large model. And number two, I want to get the model good at recognizing cats versus dogs. Not a huge deal, just two good examples. And of course, this is not a large language model. This is going to be a vision transformer. So we're going to be doing this with images. First of all, I start by creating a few helpful functions that I'm going to be using throughout my notebook. They're not a big deal. The first one here is just going to tell us what the size of a model is in megabytes, so I can show you the savings, which are going to be like really, really big. By the way, the original vision transformer that I'm going to be using is 346 megabyte on disk. Okay, so just keep that in mind. 346, let's call it 350 megabytes on disk. So this function that I created here is going to help us just print the size of the fine-tuned versions or the LoRa adapters. You can see like the savings, how big they are. This function here is going to show me how many parameters we're going to need to train. And the reason I use it is to show you the comparison of, hey, this is the original vision transformer. How many parameters do we have there? Versus how many parameters do we actually have to fine-tune when using LoRa. So you can see also the savings in the number of parameters. This is a function to just split a data set. Just get a 10% of that data set, set it aside for testing purposes. And this is a function that's going to create a label mapping, and I'm going to explain what that is in just a second. All right, so after I define all of those functions, then I'm going to be loading those two data sets. I'm going to be loading those data sets from Hugging Face. There are multiple data sets there that you can do this on. I'm just using the food data set number one and the Microsoft cats versus dogs as data set number two. Now, loading the data sets is the same process. The only thing that I'm doing here that's different is for the second data set, the label column is called labels with an S, plural. So just because I'm going to be using the same exact process to fine-tune my model on both data sets, I just renamed that labels to label, just so both data sets have the same columns and I can use exactly the same process. So after I load the data sets, I split them. So I get data set 1 train, data set 1 test, and data set 2 train, and data set 2 test, okay? So nothing fancy there. All right, so after doing that, I'm going to be creating the mappings. And again, the mappings are just two dictionaries. Let's look at the function here really quick. So I have two dictionaries. And one is a mapping from label to ID. So it goes from the name of the label, let's say it's pizza, to the ID 3. And the name of the label, which is chicken wings, to the ID, which is 4. That's the mapping, right? From label to ID. And the second mapping is the other way around. It goes 3, value is pizza, 4, value is chicken wings. By the way, I don't know if those are the actual values, but just to illustrate what the idea here is. We need this because when we are creating these models in order to fine-tune them and in order to load them so they can actually solve classification problems, the process of loading them and preparing them needs to create heads to do the classification, and that uses the mapping to just do that. So just keep that in mind. It's something that you can read a little bit more under this link. So I have a link here for pre-trained config, and I tell you exactly where to go if you want to understand more how those mappings are going to be used throughout my code. All right, so I'm going to create those two mappings, and then I'm going to create this configuration. This dictionary is going to help me basically train or fine-tune both models by just using one section for model 1 and one section for model 2. So this is just saying, hey, when I'm going to fine-tune model 1, I'm going to be using dataset 1 for train, dataset 1 for test, etc., etc. The differences here are the number of epochs. For the first fine-tune process, I'm going to use 5 epochs. For the dogs versus cats, I'm just going to use 1 epoch because that's good enough. I get high enough accuracy at that point. I don't need to keep fine-tuning after that. And the other thing that is different here is just the path where I'm going to be storing these adapters. So obviously when I finish the fine-tuning process, I'm gonna be saving the adapters to disk, and I'm gonna be saving them, both adapters, to two different folders. All right, so after doing this, I need to pre-process the images. So I'm gonna be loading an image processor right from the folder where the base model, the vision transformer was created. So now I'm gonna be defining the steps that I'm gonna be using to do the pre-processing on my side. So I'm gonna be using the specification plus specific steps that I want to define to pre-process my images. Now, keep in mind, this is not optimized. My goal here is not to get the best result for neither one of those two data sets. I'm even using the same pre-processing steps for both the cats versus dogs and the food items, okay? My goal here is just to keep the code to a minimum to show you the point that I want to show you, which is LoRA and how you can load those adapters, etc. So if you wanted to do this a little bit better, you could. You can find a better pre-processing step here just to do that. So what I have here is just a pipeline that's gonna do the pre-processing that resizes the images. And notice here that I'm using the size specified by the image preprocessor that we just loaded. That's gonna be 224. I'm centering the image, so I'm doing some movement there. I'm turning that into a tensor, and finally I'm normalizing the image using the mean and the standard deviation specified by the original preprocessor, okay? This is my pipeline. And then I have a preprocess function, which is the one that we're gonna be using at the time of preprocessing the images before sending them through the model. And this is just gonna get a batch of values, and it's just gonna call the preprocess pipeline, converting each image to RGB, and for every image in the batch, just convert it to RGB, take it through the pipeline, and add it to a batch with pixel values. That's gonna be the key on that. Just very simple. And finally, what I do is I go through both models that are in my config. Remember, the config has two keys, one for each model that I want to fine tune. And I'm gonna grab the train data, and I'm gonna specify that the transformation process for the train data is just gonna be the function that I just created, right? This function here. And I'll do the same for the test data. And because this is within a loop, that's gonna go for both models, it's gonna do these two steps twice. So one for model 1, dataset number 1, one for model 2, dataset number 2. Okay, so that prepares everything. That gets my data ready for both datasets to do the fine-tuning process. Let's do the fine-tuning process now. All right, so how do we do that? Well, first, here I think I have a few functions. Yes, so I have a few functions here that I'm gonna be using during fine-tuning. So the first function is the collate function. And what this does is basically gets a batch of data ready to be processed by my model. So as you can see, prepare a batch of example from a list of elements of the train or test datasets. So I'm gonna be passing that list of examples, and this just does the transformation using Torch to just stack the values in a way that my model understands how to process them. Not a big deal. This is sort of like a plumbing function that I need just to do the processing. The compute metrics, this is the one that's gonna compute the accuracy of a batch of predictions. So I'm gonna be using accuracy here to understand whether my fine-tuning process is working or not. And this just compute metrics is the function that's gonna do that. So I pass this parameter here, and from there you can see how I get the predictions and how I compute the accuracy. All right, the get base model, this function that I created here, it's basically loading the model from the model checkpoint, the original vision transformer, Google Vision Transformer model. So this is loading that model in memory. Notice how I pass the mappings that I created. So when I load that model, because this is gonna be a model for image classification, I need to prepare that model with a head to do classification. And to do that, I'm gonna need to specify the mappings here, all right? So not complicated to understand, loads the original model. This is the function that I'm gonna use to fine-tune the model first. And later on, when we're ready to do inference, we're gonna be using this function as well to load that model once in memory, okay? Finally, this function here builds the LoRA model. So this is what we are going to be actually fine-tuning, okay? So this is how it works. So first of all, I load the base model. So I'm going to load the big model in memory. Then I'm just going to print the number of parameters. So this is just so you see the log, how many parameters has the base model? How many parameters do we have to fine tune from the base model? Then I'm just going to create the configuration. Now remember in the images that I show you that I only show you rank 1 image matrices. So if we go up, you'll see here, when we decomposed this big matrix, I show you 2 vectors that multiplied together will give you the big matrix. These 2 vectors are using rank 1. There's only 1 column vector here and only 1 row here. Of course, the lower the rank, the bigger the trade-off, because the harder it's going to be accurate with the fine-tuning process. So if you want it to be more accurate, you could increase the rank. So for example, rank 2 will give us a matrix that will have 5 rows and 2 columns, and a matrix that will have 2 rows and 5 columns. And that will be a total of 20 values. So we will have 20 values to represent 25. So you can be way more precise with a higher rank. Now, in the paper, what they talk about is that after rank 8, I think, or maybe between rank 8 and 256, they found out that it really doesn't matter, that you can get very good approximations around that range. So you don't need a huge rank just to represent, to get a very good fine-tuning process. For this example here, I'm going to be using rank 16. So if we go back to the function, you can see this R, that's the rank. So I'm using rank 16 to represent these adapters, okay? I could go lower than that. I could go to 8. We will get similar results. All right, so here are a bunch of other hyperparameters. The alpha, if you want to know how the alpha works, you can take a look at the paper. It's basically when you add up the adapter to the original weight, how much that adapter matters. Like you multiply it, basically you're gonna multiply that, and depending on how big the alpha is or how small it is how much that is going to change the original weights. You can read more in the paper. What are the modules that we're gonna be modifying? The dropout, the bias, and the modules that we're gonna be saving is gonna be the classifier. So this specifies how I want to do LoRA. And now I can use this function, which is GetParameter Efficient fine-tuning process. I'm gonna pass the original model and the configuration of LoRA that we just defined. And this is going to give us the actual model that we are going to be fine-tuning. And in this case, right after this line, I'm printing how many parameters has this model. And you're gonna see the results as soon as I call those functions, but they're gonna be way fewer parameters, okay? Way fewer parameters because we are using rank 16 for the adapters, so those are gonna be smaller matrices. All right, so the next line here just specify a batch size, and these are all of the parameters of the training process. In this case, it's just gonna be fine-tuning. And you can go through all of those parameters. They're really not that big of a deal. Let me see if there's something here worth mentioning. The metric that we're gonna be using is accuracy. The learning rate is right here. The batch size is 128. We're gonna be using float point 16 to do this training. You need a GPU to do that, by the way. So not a big deal. That defines the arguments. Here is where the fine-tuning process happens. Notice that I'm gonna go for both models. So I'm gonna do fine-tuning right one after the other. So I'm gonna get first the first model, and I'm going to say, hey, set the number of epochs that I want for this model. Remember, for the first data set, 5 epochs. For the second one, it's gonna be 1. Then I'm gonna configure a trainer, and the trainer, the first parameter of the trainer is which model are you gonna be fine-tuning. And this is what I'm passing the result of the build LoRA model function, which is gonna give me that LoRA model to fine-tune. I pass the arguments, I specify what is the train data that I'm gonna use for fine-tuning, what is the evaluation data that I'm gonna be using to evaluate the fine-tuning process, what is the tokenizers that I'm gonna use. In this case, it's gonna be the image processor that I loaded. How am I gonna compute the metrics, which in this case is just gonna be the function that I created before with compute metrics, and how I'm gonna be preparing the data just to take it through the model, and that's the collate function that I created before. So again, It's just putting together the Lego pieces that I built before just to get them at this point. And then I'm gonna just train my model. This is gonna do the fine-tuning process. When I'm done, I'm going to evaluate the model. This is just gonna be running evaluation here. And finally, I'm just gonna print the accuracy. After I finish training and after I finish evaluating the model, I'm going to be saving that model and printing the size on disk of that specific saved model. Remember, this saving here is just saving the LoRA adapter, not the huge model, but just the adapter. So here are the results, which of course I'm not gonna run here on camera because they will take forever. Here are the results that we are going to get. I want you to read this specifically, okay? So the base model trainable parameters, okay? When we loaded the original model, the vision transformer, it has 85 million parameters. That's how many parameters are trainable. 85 million out of 85 total, that's 100% of parameters are trainable. So doing just regular fine-tuning, we will have to train or fine-tune 85 million parameters. Instead, we're gonna be doing LoRA. So LoRA trainable parameters are only 667,000, which is 0.77% of the original model. That's nothing. That's why we can fine-tune these models so freaking fast. Okay, all right, awesome. So that will be the first one. It goes through all of the epochs here. You can see the accuracy going up to 94%. You can see the evaluation accuracy is 0.946. And the size of the model, remember, we had 346 megabytes, the original model. The size of this adapter in disk is only 2.7 megabytes. Only 2.7 megabytes on disk, which is nothing compared to 346. So I'm doing just the same thing for the second one, for the second data set. You get all of the results. So this is the interesting part, because now I have the small adapters and I have the big model. I don't have to load the big model multiple times when I just need to change, plug and play the adapter on that model. So this is what I'm doing. I have a function here that's called build inference model, okay? And I'm gonna pass the mappings that I need to configure the heads, the classification heads, and the adapter path, or the path where the adapter is. So I can just load the model using the get base model that just goes and loads the original model. And then I can just build a parameter efficient fine-tuning model. So using this class, using the from pre-train, I can pass my model and the adapter. And this is going to return an already modified or fine-tuned model that specializes on solving one specific task. And that is just amazing. I did not have to modify the original big model at all. The original big model is the original big model and stays unchanged. I only had to create the adapter and then plug and play that adapter at the time of using it. So this is that function. It's gonna create an inference model. And there is a predict function here. I'm gonna pass an image to that function, the model that I'm gonna use, and the image processor, because I obviously have to pre-process that image before I send it to the model. So internally, what I do is I just process that image, and then I go and compute the outputs, get the logits, and just find the most important item on those logits. This is a classification head, and just using the mapping, I can get what the name is. So, hey, given this ID, what is the name of that class? So I use the ID to label mapping. So very simple function here. Let's go to what's gonna happen now. I'm gonna add some parameters to the configuration. So what is the inference model that each model is going to use, and what is the image processor that each model should use? And here, by the way, both of them are using the same image processor. I just kept this just in case I wanted to just make modifications before, but right now, both are using the same image processor, both data sets. This is very simple. Here I have a few samples. So this example here is, I guess we're gonna have to open this. Chicken wings. These are chicken wings. Let's see the second one. This is just a little cat. The third picture is just a dog. And the final picture is a pizza. Okay, so I have 4 samples, and notice that I'm specifying this is an image and this is the model that I want to use to classify this image. So for the chicken wings and the pizza, I'm gonna be using model 1, which is the one we fine-tune on food items. And for the cat and the dog, I'm gonna be using model 2, which is the one we fine-tune in the cat versus dogs, okay? So these are my samples. And this is just a loop. I'm gonna go through all of the samples and I'm gonna be doing the following. I'm gonna be opening the image URL, okay? I'm gonna get that image URL. I'm gonna grab the inference model and the image processor from the specific model specifying this sample. So the sample says model 1. So I'm gonna say, okay, just give me the inference model that's specialized on this task and give me the image processor. And then I'm just gonna be computing the prediction. So just give me a prediction given this image, this inference model, and this image processor, and print that prediction. And here's what I get at the end: chicken wings, cat, dog, and pizza. And that is amazing because, of course, anyone can build a classification model, but I want you to think about what's happening here. I can have my big model, one big model, do the fine-tuning process for multiple smaller specialized models and save those small adapters and load the adapters dynamically in memory as I need them, instead of having multiple copies of humongous models sitting there. That is really, really powerful. Now I want you to think about what's about to happen with this tech. As phones get more powerful, as hardware keeps going up or improving to catch up to where we are right now, we're gonna be able to do even more personalization with techniques like LoRA and QLoRA, or even newer techniques when we come up with them, where models are not just going to be specialized on specific tasks, but specialized for one specific user. So I can have a model that's fine-tuned on my data, not somebody else's data. A model that's fine-tuned in the way I write. I like my emails. I do my image changes or whatever AI helps me with. That is what we're moving with this. We're gonna have a bazillion number of adapters, small adapters, that we can plug and play with a big model to help us use that model to perform multiple tasks. Again, you can find the source code here in the description below. Hopefully this explanation made sense. Leave me a comment if there is a question that you have, if there is something else that I can explain, or what you want the next video to be, and I'll be right there with you. I'll see you in the next one. Bye-bye.